Hi everyone, I'm Pingcheng, a PhD student from the US. Today, I'm very glad to discuss my research work. The goal of our work is to apply the well-established database techniques into blockchains. Specifically, we focus on execute order validate blockchains, EOV for short, like Fabric. Our work is targeting on the transaction execution layer, which is in the same spirit of Fabric++ in last year's SIGMOD. Our research is motivated by our subtle observation on their strong serializable behavior of execute order validate blockchains. Strong serializable prevents more parallelism than serializable level. We explore the transaction reordering techniques common in databases to achieve serializable transactions in blockchains. The major feature of our work is that we principally borrow the transactional analysis from optimistic concurrency control for the reasoning. We implement our reordering techniques from original Fabric into Fabric Shop and open source it. We achieve 20% improvement over the state-of-the-art. Our approach can also further complement with other Fabric implementations such as Fast Fabric. The pipeline of EOV blockchain is separated into 3 phases. In the first phase, a peer simulates a contract call against the state after block and returns the result. The result consists of the read keys, their versions, updated keys, and their installed value. The second phase reaches consensus on the transaction order and buffer them for the pending until the block formation condition is met to create a block. The last phase first checks that the transaction read records are still up to date and then apply the install update. Due to the validation step, a block may contain aborted transactions, which reduces the system throughput. We observe with the increase of the skewness of the modification transaction, a substantial fraction of transactions are aborted. Worse still, the overall throughput remains constant due to the inherent system bottleneck. This observation illustrates the necessity to streamline the transaction schedule to reduce the transaction abort. In OCC databases, each transaction is assigned with the read timestamp, which determines the state exposed for the query. An end timestamp is similarly assigned during the commit. A validation step with respect to 2 timestamps and the access records determines the status of this transaction. The following figure demonstrates 6 canonical transaction conflicts, 3 between concurrent transactions and the rest between 3 non-concurrent transaction pairs. For example, if the previous and the later non-concurrent transaction rise to the same key A, it will form an in-write-write conflict. According to the conflict serializability theorem, the effect of the serializable transaction schedule is equivalent to any serialized transaction history that respects the conflict order. A transaction schedule with any conflict cycle is unserializable. Now we describe how blockchain EOV pipeline is similar to OCC in databases via the concept mapping. We define a blockchain snapshot as the state after block M, and the snapshot sequence number is a 2-value tuple n plus 1 and 0. For EOV blockchain transaction, its start timestamp is the sequence number blockchain snapshot as it simulates on. Correspondingly, the end timestamp is a 2-value tuple consisting of block number and transaction position in a block. Note that the end timestamp is determined by the consensus. We simply inherit the concept of concurrency if both transaction execution interval overlaps. It is easy to see that any pair of transactions in the same block is concurrent. We further define a transaction schedule is strong serializable if it conforms to a serialized schedule. Secondly, that serial schedule is exactly ordered by the transactions and timestamp. Note that the serializable level does not require for the second restriction. We demonstrate a transaction schedule without anti-rewrite conflicts achieve strong serializability. The crux of the proof is that the anti-rewrite is the only conflict that relates later transactions to earlier ones. Given this, Fabric and Fabric++ both achieve strong serializability simply because their validation step prohibits anti-rewrite conflict. Given above, it naturally asks, under serializability instead of strong serializability, how to reorder pending transactions before batching them in a block. Note that the consensus has first established a primary order. Reorder here changes a transaction position in the new block. It is equivalent to adjust for the end timestamps and their relative commit order. Now we lay out the two lemmas. The first states that the reordering does not impact on the commit order and the conflict order of non-concurrent transactions. The second is that the transaction does not change its concurrency relationship with respect to others after reordering. We omit the proof here. The insight is that we can safely focus on the reordering's implementation to conflicts between concurrent transactions only. There are only three conflict types between concurrent transactions: C rewrite, anti-rewrite, and C write-write. The third lemma states that the conflict order preserves between C rewrite, anti-rewrite, but not C write-write when switching two transaction commit order or position in a block. These can be easily seen from the figure for their transformation. Now we are able to develop the theorem that the transaction schedule can never be reordered to be serializable if there exists a cycle with no C write-write conflict between pending transactions. We omit the proof here, but we lay out one example respectively for one unreorderable and one reorderable schedule here. Note that in the above unreorderable scenario, the conflict order still preserves by switching transactions with a C rewrite or anti-rewrite conflict. Hence, the conflict cycle is unavoidable. However, such cycle can be broken by switching the transactions with C write-write. Given the above theoretical insights, we can easily deduce our serialized concurrency control. We first simulate the transaction execution against a particular block. During the ordering phase, when new transaction T arrives from the consensus, we compute for all conflicted transactions with respect to the transaction graph G, except for the C write-write conflict among all pending transactions P. If there exists such a cycle, we directly abort it due to its unreorderability as guaranteed by our above theorem. Otherwise, we incorporate the new transaction T as well as the computed conflicts into the transaction graph G. When a new block to be formed, we topologically sort P with respect to G. The result order determines the transaction position in the new block. Note that since the G is acyclic, P as a subgraph is also acyclic. Hence, P must have a topo sorted order. No transaction need to be aborted here. We at last restore C write-write conflicts from the ordered P and incorporate them into G. Suppose safety and liveness holds in the original consensus. We argue that our reordering preserves safety as it is deterministic. No honest peers will diverge as long as they perform the same reordering procedure under the same identical transaction stream. However, liveness can be compromised as the reordering logic is public. A malicious peer could bias the consensus service on the primary order to abort certain undesigned transactions and later reordering phase. This can easily be mitigated by relying on the transaction hands to establish the primary order and later review transaction contents for the reordering. Now we start to discuss how we exactly implement above concurrency control on Fabric, resulting into Fabric Shop. The left diagram illustrates our major instrumentation along the transaction pipeline of Fabric, which basically reflects our above proposal. In the following, we elaborate on the techniques to achieve snapshot consistent simulation, compute transactional conflicts for a new transaction, detect for the syncing schedule from a transaction graph, and restore serializable conflict back to the graph. For the snapshot consistent simulation, the major challenge is to parallelize the transaction execution with the block commit. Despite both steps need to access the state from level DB, in the original Fabric, above steps are mutually exclusive as the state access is coordinated with a single global lock. In our Fabric shop, we rely on the snapshot support from the underneath level DB. In particular, whenever a block is committed, we create a state snapshot. A transaction is simulated on the latest state snapshot at its start. Even though during the execution, a new state snapshot is created for a new block, this transaction continues to use its current state snapshot determined at the start. To efficiently compute the conflicts for a new transaction, we employ a multi-version storage at the order side. The storage consists of two data items, committed write transactions, CW for short, and committed read transactions, CR for short, to index previously committed transactions. The key of CW consists of the concatenation of a record key and the commit sequence of the transaction that update this record's value. Similarly, the key of CR consists of the concatenation of a record key and the commit sequence of the transaction that reads the key's latest value. In the memory, we also use pending write transaction PW and a pending read transaction PR to index pending transactions with these access records. Due to this special data organization, for a new transaction with read set R and write set W, we can easily use the following formula to compute the conflicted transactions, such as anti-rewrite and so on. The node of a transaction graph is a transaction, conceptually, and its edges are conflicts. To effectively represent a graph, we implement a graph node as an array of pointers to its immediate successors, and a Bloom filter that encapsulates all the transactions that can reach this node. Hence, given a new transaction, we can easily loop through each pair with predecessors and successors and test with the Bloom filter. Any positive indicates a syncing schedule, and thus we should abort this transaction. At last, given a topologically sorted schedule of pending transactions, we restore serializable conflicts to the transaction graphs, which essentially add new edges. One prominent issue is that the connectivity of a transaction may be affected by multiple write-write dependencies, but our technique in a fabric shop is capable to perform the update in a single iteration. We decide not to expand the nitty-gritty details here due to the time constraint, and we will also not to discuss how to limit the transaction graph in an acceptable scale given the forever coming transactions. In the experiment, we evaluate our fabric shop with 4 baselines, 1 fabric plus as the previous state-of-the-art, the original fabric, 2 fabric variants that equipped with 1 standard and 1 latest OCC technique from databases. Each transaction in a workload reads and writes 4 distinctive records with a configure ratio to touch on 10% hot records. In the first experiment, by varying the block size, we observed that our fabric shop achieved the optimal at 100 transactions per block at our testbed, while others are 200 or 400. It is worth mentioning that the fabric shop attains the lowest latency at small blocks. It is because fabric shop aborts transaction earlier at the ordering phase. Such design effectively avoids throttling the bottleneck at the later validation stage. In the second experiment, we varied the write-hard ratio and their respective optimal block size. Notably, fabric shop constantly outperform other baselines. From our internal fine-grained timing, we observed that fabric shop spends significantly less time to process a block than other baselines. In the third experiment, we repeat the same setting but vary the read-hard ratio and measures the processing time for each transaction. Our fabric shop can still get the best performance, but the results shows that the most delay of fabric shop is attributed to the individual transaction processing. Then, we increment the client delay to simulate the network latency. As expected, the above ratio all increased for each implementation, as the longer transaction delay generate more conflicts. Note that when conflicts are too heavy, most implementations achieve similar performance, as they all reach the theoretical limit determined by the workload. Next, we increment the access interval to simulate the execution-heavy transactions. The performance gap is still very clear. Note that the declining red curve in the right figure. It demonstrates that the original fabric's remarkable degrading performance when the transaction simulation time increases. This is easy to imagine, as the original fabric prohibits concurrency between transaction simulation and block commit, as explained above. In the last experiment, we also apply our concurrency control into Fast Fabric, the latest implementation of Fabric protocol. It results into Fast Fabric Shop. We compare both implementations under the standard small batch workload. Observe increased account workload, which is write-only with no skewness at all. Both approaches achieve similar performance. It indicates that our concurrency control imposes minimum extra overhead when the workload has no conflicts. With the increasing skewness, our performance gain is gradually increasing, up to 66% when the Z-fine coefficient goes to 1. From the right chart, our performance gain is because we can recover transactions with anti-rewrite conflicts, none of which can be serialized by the original fast fabric. This experiment shows that our concurrency control technique can complement with other implementation-specific optimizations. Thank you.